Today I'll try to teach how to use basic circuit analysis to solve this example circuit. So the first analysis method that we're going to use is KCLs. So in order to use KCLs, we're kind of looking at the voltages and subtracting them to find the current. I'm just trying this out. I'm not really experienced in teaching, but we'll see how it goes. So for this circuit, we're going to try to find Vx, which is at the bottom, the blue bottom. And with this circuit, we can see that the ground is at the top right. So I like labeling them. For KCL, we kind of use nodes, which are just like wires in a way. Like for ground, the node would be described as what I'm highlighting here, including the ground. I just didn't feel like going over the ground. But this would be one node, and this node represents 0 volts because it's associated to ground. And Vx is another node, which is represented by the highlight around here. This all represents the Vx node, which we're trying to obtain. So with KCL, we established that down here is Vx, right? And next, there's a power source over here that we can use, because if you go through it using KCL, the way I was taught was just that the top node is kind of what you use. It'd be like a -10 here. So it'd be, if you go through it, this node will turn into Vx minus 10. And by the way, this node is just this small thing right here. And as for this other power source, because right here, there's a short happening right here. There's nothing really to go through. This kind of just doesn't do anything. It's like a 0. And also for this resistor too, because there's no current going through there, there's also 0 because of the short. So this should be pretty easy. We'll start right here at Vx minus 10. The reason we start there, not there. We start at 0 volts, sorry. We wouldn't start at Vx minus 10 because there is a voltage source here. And with KCL, I was taught don't use it around voltage sources. So we're not going to use it through there. And that's also the case with Vx. We wouldn't do it with Vx because we'd have to go through this voltage source again. So the only place we could actually do it is ground. So let's write our KCL at 0 volts. So the first thing we encounter as 0 volts is this current source. And because it's leaving, it's going to be a positive 1/5 amps. Let's say this current source was facing towards the node. This would be a negative 1/5 amp. I'm pretty sure there's like a more detailed explanation as to why, but I don't really remember why. It's just kind of convention to do that. But so with our KCL equation, we first start off with positive 1/5 amps. And the next thing we encounter is this resistor. So right here there's 0 volts as we established because that's the node. And next, the other node over here is Vx. So in order to find what we're trying to find right through here is the current that goes through here. And we can describe that current by 0 minus Vx over 20, because just based off the convention of V equals IR, we're trying to find the R in this equation. So to find R, it'd be V over R. And what we're doing is finding the difference between this voltage and this voltage and putting it all over the resistor. So the V here would be 0 minus Vx, and next the resistor would be 20. And the reason we're putting 0 first is to make this current be positive, in that sense that it goes away. That's why we start with the 0 minus Vx. If we did Vx minus 0, we'd be establishing that the current is going this way, and so this whole thing would have to be described as negative. And next, the next thing we encounter is this 30 ohm resistor. But because there's 0, there's nothing there, we could just put plus 0 here. And the final thing we encounter is this resistor. As I mentioned before, we're gonna do this. This right here is 0 volts. This node is 0 volts, and this other node is Vx minus 10. And because we just want to do it positive, fake going away, make the current source go away, we do 0 minus Vx minus 10. So let's write that down in our equation. We do plus 0 minus, and put it in parentheses because we will have to distribute the negative, Vx minus 10 over the resistor that we did that through. So that would be the 40 ohm resistor. And next you make it all equal to 0. And there's your equation. Because there's only one unknown, we only have to do one equation to find this unknown. And this is just arithmetic, just simplifying it. What I like to do is I like to remove the bases down here, the denominators. And the common denominator that I found would be this highest 40. So we multiply everything by 40. And next, because we're multiplying everything by 40, it'd be 40 times 1/5, which is just 40 divided by 5, which would be 8. Plus, and next 40 divided by this 20 is just 2. So that would be 2 times 0 minus Vx. And next 0 stays the same. And next we do plus, and because it's 40 divided by 40, which is 1, you don't multiply anything for it. So it'd be plus 0 minus Vx minus 10, which would equal to 0. And from here, you just keep doing simplifications. So 2 times 0 is 0, so you could just remove that. It wouldn't be a plus, it'd be minus 2Vx, because we distribute this 2 to the Vx. And next we can ignore these zeros. And next you find another minus Vx plus 10 is equal to 0. So this would be 18 minus 3Vx is equal to 0. And we generally want this Vx to be positive, just for namesake, I guess. So we do 18 is equal to 3Vx. We divided that by 3, divided that by 3. And we find that Vx is equal to 6 volts. Now, this is the way to do it through KCL, and if you're not very familiar with this method, then I can understand that's very daunting, because it was to me daunting when I first learned it. And the method I was more comfortable with was KVLs. So with KVLs, we're trying to still find Vx, but this time, the way I was taught is just that you have to put where your currents are going, basically. So we have this 1/5 amps right here, this current that goes 1/5 amps, and through all here it's 1/5 amps. And we know that because it's 0, this has 0 amps going through it, so we don't need to add or subtract anything. So we know that through here also it's 1/5 amps. Now, there's a problem in this circuit. Oh, there's not really a problem, but the thing with this circuit is just that we can't just use one current because there's no current going over here. So we have to put our own current, and I'll call it Ix. So Ix is going through here all the way right here, Ix. And Ix is also going through right here too. And as we described last time, this is 0, and this is also 0 because there's no current going through, just because this is a short. So in theory, honestly, if it makes it easier for you, you could just erase it. It'll look much simpler like that. As you progress through, though, there is different circuit analysis where you can't really do that, where like you might put Vx or Ix or something, plus or minus Vx or Ix, to find some voltage through there. But for this circuit and for just basic analysis, we could just take them off, honestly. Now, there's a problem here. Right here in this resistor. 20 ohms, right? So we need to describe what currents go through it. And for me, I say that the 1/5 current goes all through here. So it'll go 1/5 amps, 1/5 amps, 1/5 amps, 1/5 amps. So we could say this goes 1/5 amps. But also this Ix is going through here. This 1/5, the current source makes it so only 1/5 can go through here. So Ix only has one place to go, which is through the 20 ohm resistor. So because there's two currents going in opposite ways, you can kind of decide which way you want it to go. So for me, I prefer making it go up. So it'd be 1/5 minus Ix because it's going the opposite way. You could also put it going down, which would be Ix minus 1/5. It's up to you. It's really the same, honestly. Just at the end, you're gonna get a negative or a positive depending on which way you do it. But for easier sake, I said 1/5 minus Ix going up. So now that we have our currents all described, we could do the KVL equations. I'll do the KVL equation around the outer edge, but also the inside, kind of like where I have it in pink. You can't really do KVL at current sources because there's only one current going through and there's not really much of a point going through there. But I'll do it at our outer edge. So I like to start at the bottom left corner, and I'll be going up through here. So the first thing we encounter is a 10 volts. Compared to the KCL, you could just take the first one that you see. So this would be a plus 10. And next we go through the 40 ohm resistor. And because current goes from plus to minus, we could say that this is plus 40 times Ix. The reason it's because of that is because of Ohm's law, which is V equals IR. And we're just trying to find the voltages through here. It is Kirchhoff's voltage law, so we're trying to find voltages. So this would be Ix times 40 ohms, which would be the voltage. And that's why we put 40 times Ix here. And next, we continue going our way. And the next thing we encounter, we go down because we can't go through this current source. So we go down is this 20 ohm resistor. And actually, I'm going to use this convention. You can still do this too. Just that if you do that, it'd be plus to minus. So in that case, how I said earlier, it'd be minus 20 times 1/5 minus Ix. I'm going to just do that. You could also just do, if you're doing it this way, it'd be plus to minus. So that'd be plus 20 times Ix minus 1/5. I mean, there's not much of a difference, so it doesn't really matter. But as you continue, you go to the left here. And because you still can't go through the current source. So you get back to where you started, and that's your equation. And next you make it equal to 0. And next you start simplifying. 10 plus 40 Ix minus 20 divided by 5, that's 20. 4. Sorry. Minus 4 plus 20 Ix is equal to 0. That's 6 plus, combining like terms, 60ix is equal to 0, and 60ix is equal to negative 6. Divide that by 60. And ix is equal to negative 0.1. And now we know that ix is negative 0.1. So back to using Kirchhoff's voltage laws. In order to find this Vx, we need to find the... Here, let me clear it up a little bit here. We need to find the voltage that goes through this 20 ohm resistor. So as we stated, this is plus and this is minus, and the current that's going through here is Ix minus 1/5. So let's find that voltage that goes through it. So we go V is equal to 20 times Ix minus 1/5. And we found what Ix is, so we can plug that in. It's negative 0.1 minus 1/5. And the voltage that goes through there is, let me do the calculations real quick. 0.1 minus 1/5. That is negative 6 volts. Minus 6. So we found this voltage, so now we can find Vx. We do unfortunately still have to use a little bit of KCL here just to find the voltage difference here, because with KVL you can't really find Vx, a certain voltage. But we just say that, as we stated earlier with KCL, this is a 0 volt node, right? So right here it's 0 volts. And right here it's Vx. And we're just trying to find the difference through here. And you can pretend this negative 6 honestly is just a voltage source. So we'd label it as plus minus negative 6. And because of the convention I said earlier about the sign convention, where you use, for KCL, you use the bottom one, or like the opposite one that you come in through. So like, sorry if I didn't describe that right. So since we were going from the bottom, we won't use this this first one, we'll use the second one. And because we're coming from the top, we're not going to use this positive, we're going to use this negative. So using KCL to find the Vx, we go 0, and next we would get negative 6. Because it is a negative 6, and we just add a negative there, which would turn it into Vx is equal to 6 volts. And that checks out because we got it the same way both times. And yeah, that's kind of how you do it. I'm not sure if I described it right, and I do apologize if I did, but I remember when I was first starting in electrical engineering, I was kind of struggling on how to do these types of equations and what everything meant. But I hope this helps someone out, and if you have any questions, please leave a comment down below, and thank you for watching.